All right, so what do we know? What's new? Again, that's sort of a structure I like to keep. So what is a limit? And is a question that we took a look at on Monday, as well as a little bit today. And then how do we find limits graphically and algebraically? Okay, so we talked about how we find it from a picture, and then we talked about all the different methods that we could use algebraically. Primarily, we have substitution, we have conjugates, we have factoring, and we also have fractions. Right, so there's a few different methods that we know how to do algebraically. Now, one other thing that's nice about the what we know is that this list of questions should be something, as you're thinking about like how to prepare for an exam or like what was really important from the previous lecture, that will sort of give you that information as well. Okay. All right, so what's new? We're going to talk about a couple concepts today. Okay, one thing you'll find is that Calc 1 is very heavy on the concepts. Like it's so important that we understand what and why we're doing things. And so the main focus for the second part of class is talking about something called continuity. And because we're talking about limits, how does it relate to limits? All right. We're also going to dip our toes back in the pool of trigonometric identities. All right, so for better or for worse, trig is one of those things that does not go away. In fact, we use it quite a bit in both this class as well as the entire calculus series. Okay. All right. So what is continuity? This will be something that as you work on this activity on your own time, I would encourage you to sort of think about like what main concepts you see, but also what questions you still have about it. Okay. Now, initially I designed this to be a small group activity, but again, based on time, one suggestion, if you don't want to work on it by yourself, is in Discord, there should be a, let me just make sure I set that feature up. There should be something called a voice channel. Okay, it's like at the very bottom. The voice channel, people can hop on. I believe you can also do a video version of that, right? So it's sort of like Zoom, except it's built into Discord. And so it could be one place where you could get a group of people together and be like, let's just walk through this activity together and just talk about it with each other. You could also ask about this at tutoring or at office hours, right? So none of these activities are really meant to be like just on your own. You can certainly always find support for that, okay? But as we sort of move into what we mean when we talk about something continuous, all right? So let's go ahead and actually do example 1 first, all right? So we're gonna look back at example 1, then we're gonna talk about this definition, and then we'll get a chance to practice it, okay? So let's take a look at this example. And we have the same picture that we had yesterday. And some of these questions are the same and some of them are different, okay? And so looking at this particular graph, what will we say f of 0 is? All right, I agree that f of 0 is 3. And if we were to give a reason for that, what might we say? Yeah, it is the filled in circle. It is not the open circle, right? Exactly, or the solid dot, perfect. And if we were to translate this f of 0 equals 3 into words, we might say when x equals 0, then y equals 3, okay? All right, what did we say the limit as x approaches 0 of f of x was? okay, that it does not exist. It does not exist. Why does the limit not exist?
There's a hole.
There's a hole. I say though, it's not just the hole, and it's not just because there's a piecewise function. There's actually something really special about the way this is designed.
Is it because like from the right and from the left, they're not like meeting up at the same point?
Ah, there we go. There we go. When we come from the left-hand side, we get close to 1. When we come from the right-hand side, we get close to 3. Those are different values, okay? So if we wanted to say B in words, we might say the overall limit does not exist because, and I'm going to abbreviate here, the right-hand limit, okay, so RHL, right-hand limit, does not equal the left-hand limit, or LHL. Okay, so from the left, I get to a value of 1, but from the right, I get to a value of 3, and those are not the same value, so the overall limit does not exist. All right, well, based on your answers from part A and B, what do we think about C? Does f of 0 equal the limit as we approach x equals 0? No, right? No, because 3 does not exist. Okay. Well, let's look at question D. Is f of x continuous at x equals 0? What are our thoughts? Without having really looked at a definition of continuity, would you say that it's continuous? I see a bunch of no's. This is excellent. Someone tell me why. Why does your gut tell you that is not continuous? You don't have to use mathematical language here. All right, we've got all the values are different, right? And a more visual way of looking at it, a little bit more geometric, because you can't trace the line, okay? And I really like that sort of last one as a visual for what it means to be continuous, okay? So this part of the graph, just the part where the red laser part is that part continuous? What do we think? Yeah, I could just, I could just draw that part of the line. I don't have to pick up my stylus or my marker or my pen or pencil. I could just trace the entire thing. What about this chunk? Is this chunk continuous? Ah, it is continuous. If I start just next to that hole and I trace just that part, it is continuous. But what happens if I want to do this whole right-hand side? I would have to start here. I'd have to pick up my laser and move it to the other side. Is the red part continuous? Right now it's not, because I have a disruption, a hole in that part. Okay. If I wanted to see what's happening at x equals 0, I draw this part. I have to pick up my pen or pencil and start at a different value. When we ask ourselves, does f of 0 equal the limit there? That's a good clue for whether something is continuous or not, okay? If we answer this question and we say yes, then that means that our function is going to be continuous at that point, okay? So to say, is f of x continuous at x equals 0, we could say something like yes, or sorry, no. No, it is not continuous because the actual value there, which we might say is f of 0, is not equal to the limit as we get close to 0. Okay. Let's actually do one more example before we go to this definition. All right, so let's take a look at example 2 over here. All right, so we have this function. We're going to call this one g of x. We see some weirdness happening. I would hope that our eyeballs are sort of drawn to this -1 situation. That looks weird compared to just this part over here. Okay. And the question I'm asking is this function continuous at x equals -1? Right? So don't answer yet, but go ahead and type either yes or no into the chat, like yes, you think it's continuous, no, you think it's not, and I will tell you when to hit enter or return, right? So take a moment to think about whether you think the function's continuous at x equals -1. And in 3 and 2 and 1, go ahead and hit enter. All right, very effective chat blast here. All right, so we've got a whole bunch of no's. All right, I would agree that this function is not continuous, okay? But this is the part that can be hard, right? How do we explain? We're like, well, we want to make sure that we're using mathematically rigorous language to explain this, all right? So we might say something like this. Because f of -1, what is f of -1? Let's start there. What is the y value at that point? It is undefined, I buy that. All right. All right. What about this? Limit we switched letters. My apologies. Okay. What would be the answer to this question? Okay, I see a lot of 2's. All right, so when we see the plus sign, we're tracing from the right, and it sure does get close to 2. All right. What about that? What is the answer to this limit? Ooh, all right, I see a positive infinity. I see does not exist. Any tiebreakers in the class? What do we think? All right, well, let's trace from the left-hand side, and this function goes up like this. Ah, okay. Now, it turns out both answers are technically correct. It depends what kind of mathematician you ask, Okay, so you can say that this limit is either positive infinity or does not exist. I'll tell you why you can say that in just a second. Yeah. Okay. There's sort of two thoughts. Some people look at the graph and they're like, yeah, let's go into positive infinity. So I'm going to put positive infinity. And that's absolutely fine. There are other mathematicians who are maybe a little bit more type A, or for their particular kind of research, infinity is not considered a number. And so those folks might say does not exist because infinity may not be a number. Okay. I will take either answer as long as you can explain to me why you're choosing what you're choosing. So if you are like, yep, this is going up to positive infinity, that's why I put positive infinity for that limit, that's totally fine. If you're like, yeah, it's going up, but infinity is not really a number, so I'm going to say does not exist, that's also fine. Okay. So let's make sure we've answered this question. We said that no, this function is not continuous because g of -1 is undefined, right? So the value there is undefined. The value from the right is 2, and the value from the left is either positive infinity or does not exist. Are those three things the same as each other? No, right? We've got an undefined, we've got a number, we've got a positive infinity. So we can say no because these three things are not all equal to each other. Okay. But why would it matter if things were equal to each other? Well, let's take a look at part B and see if that can answer that for us. So part B is very similar, but it says, is g of x continuous at x equals 2? So I'm going to ask us to do the same thing. Don't hit enter yet, but in the chat, type yes, you think it is continuous at x equals 2, or no, you think it is not continuous at x equals 2. And we'll just give everyone a little bit of think time. All right. And if you could hit enter with your response, and let's go ahead and see. Yes. All right. I agree. Yes, this is continuous, right? Now we want to make sure we can explain it, why we think that is. And so we're going to find these three values again and see what happens. Okay. So we can say yes, because let's start with g of 2. What is g of 2 equal to? Yeah, sure. And again, I think this is a great one where we're kind of like estimating this. Maybe call this 2, 1. If you said like 1.3 or something, like I wouldn't be mad. Just if you said 10, I would be like, whoa, I don't know what we're looking at here, right? But like 1-ish is close enough. All right, what about the right hand limit when we approach 2 from the right? What value do we get to? I agree, we also get to 1, right? Like if I start tracing here, it's gonna get close to 1, right? And don't forget about that left hand limit. When we come from the left part of this function, what value are we getting close to? We're also getting close to 1. Okay. So we looked at the value there. We looked at the right limit, the left limit, and they were all the same. And it turns out you all were absolutely correct. It is continuous here because you can draw it without picking up your pen or pencil. But a more rigorous way of saying that is because this y value matches the right-hand limit and matches the left-hand limit. Like they all get to the same place. All right, so yes, because all of these three have the same value as each other. Okay. So, are there any questions so far about how we're describing whether something is continuous or not? All right. So let's scroll back up and look at the definition now that we've had a chance to explore a little bit of what we bring to the table, right? Before someone else tells us what is this kind of math, I want to see what we bring to the table. And so we see that the textbook, and this is a screenshot from your textbook, just so I can start to introduce to you like, okay, this is what the textbook looks like. This is how it does its definitions, things like that, okay? So the function f of x is continuous at a point if and only if the following three conditions are satisfied, okay? And so we want to make sure that it is, first of all, the y value is defined, okay? This means that a y value exists for that x value, okay? A y value exists for that x value. The second thing that we want to see is that the overall limit for that x value exists, okay? And last but not least, those two values are our overall limit, we want that to equal the y value, okay? If you're missing any one of these three, you are discontinuous. So you don't have to miss all of them. You just have to have one that's different from the others, and then you're done. Okay. All right, so concept, but now let's think about how we can use this, okay? So this graph right here, for example 3. I'm going to ask you in the privacy of your own learning environment, if you happen to have space on your screen, or if you are cool enough to download the app for your phone, go ahead and type this function into Desmos. Right. And so I'll go ahead and do the same. So I'm going to go ahead to Desmos. And if we're putting in something as a big fraction, usually I like to open up parentheses, then I can put the whole thing over a denominator. So we had x squared minus 3x minus 10, and then I'm going to divide it by x squared plus 2x. Great. Okay. So we should have a graph that kind of looks like this. And my claim is that this function has two discontinuities. Two places where you cannot just connect it with a pen or pencil. Can anyone give me an x value where you think this function is discontinuous? All right, we've got one in for an x equals 0. Great. All right. And so at x equals 0, we have a vertical asymptote. Okay. Not all asymptotes are the same. And so I'm going to ask us to focus on the x value here that's causing a problem. Okay. And I can totally get why we would say, well, there's a horizontal asymptote, so that's where the other discontinuity is. In fact, however, that is not where it is. And this might require us to maybe click and sort of drag along the graph. Because remember, sometimes we get to a place where we think there's a value, but there's actually not a value. Right? Over here. Those all look like they have values. Oh. Right at 2, at -2. All right. So if you go to -2 on the graph, you will get an undefined out. I claim we can get 0 and -2 just from the equation, that we don't need to put it on decimal. Any ideas where I would get the values of 0 and -2? All good guesses. All right, so maybe the power of 2 means there's 2 values. Matthew, what do you mean by denominator? Can you unpack that for us a little bit more? Okay, so on Monday and today, we were like, well, if we have a 0 in the denominator, that's a problem for us. All right, so let me go back to the notes so we can sort of sketch this out and write this out to see how we could predict just from the equation that there's going to be asymptotes. Okay, I'm going to switch back to the other screen. Great. All right, so I'm going to make my best graph sketch here. I'm embarrassed to say when we get back into the classroom, you all are going to see how terrible my in-person live graph sketching skills are. They are not good. In fact, I think my father told me one time that I couldn't be a real math teacher unless I could draw a perfect circle on the board, and that has yet to happen. So here we are. All right. And I think we see something sort of like this on this side, and that's good enough. But the one value, the one discontinuity that we saw here was right here, right? That was a really good intuition that everyone had, that maybe at x equals 0, there is a, what we call a vertical asymptote. All right, and then when we traced along super carefully, we actually found that right about here. In fact, maybe we call this x equals -2. We had a hole. And this was different kind of discontinuity, okay? And so as a suggestion from Matthew, how could we use algebra to find this, right? Well, we can go ahead and we can factor. If we factor the denominator, we will get x times x plus 2. And if we factor the numerator, we'll get x minus 5 times x plus 2. Now, if I asked you to find the limit here, what would you do next? Yeah, you would cancel, right? What would you cancel? Yeah, we would be like, oh, we simplified, these reduced, and now we can use substitution, right? But here's what that was secretly telling us. When we got 0 over 0, that was telling us that there was a hole at where x plus 2 equals 0. Or we knew that to be negative 2. Okay. This is called a removable discontinuity. Removable in the sense that we just picked a point, an x value and a y value coordinate on the graph, and then we just threw it away, toss it away. Removable discontinuity. Okay. That's what happens when we get 0 over 0. But the other value that makes the denominator 0 is 0. There's a vertical asymptote at x equals 0. All right. And we usually refer to this as an infinite discontinuity. All right, an infinite discontinuity. We're just layering on a little bit more language that there can be more than one type of discontinuity. And if we see the same factor on the top and bottom, that's going to give us a removable discontinuity. However, if we only see the factor on the bottom, that will give us the vertical asymptote. Okay, next week, we're going to work a lot more on these vertical asymptotes. All right, we're going to come back to this again next week, but for right now, I really want us to be able to visualize the difference between those two. Okay, let me pause for a moment, see if there are any questions.
I know we're supposed to just think about this right now, but I'm like really lost on like how we went to like straight from, I know like the breaking the part down with the x plus 2, but then you kind of lost me at the whole at x plus 2 equals 0.
Okay.
Yeah.
Okay. So maybe let me write this out. Where can we put it? Let's just add a new page. Okay. So let's take this function, all right? Glad to know that the factoring part makes sense, right? And if we get rid of those colors for a moment, okay? Now let's say we wanted to get something that was undefined out of a fraction, okay? So you want to get something that's undefined. The way we can guarantee that that's going to happen is if we have that 0 that we've been like doing the green 0. Remember we said like the 0 in the denominator is the problem. If we have a 0 on the bottom, that means that our fraction is going to be undefined. Okay, so every time we have a 0 in the denominator, we have a problem. And sometimes that problem looks like a hole in the graph. And sometimes that problem looks like a vertical asymptote. But either way, these weird features in a graph happen because we accidentally got 0 in the denominator. Okay. And so Matthew's suggestion was, well, if we want to find out where the problems are, then let's figure out what makes that bottom part 0. And so I think it was Nor had said something. Sorry, I'll be better about folks who are contributing because you're all contributing great stuff. But if we set this equal to 0, this will tell us where the problem spots are. Tells us where the discontinuities are. Okay, and so we do our little equation solving. We get x equals 0 and we get x plus 2 equals 0. So the two places where we have a problem are x equals 0 and x equals -2. Does that make more sense?
Way better.
Okay,
Yeah, it
great.
clicked. Yeah.
Great,
Thank
thank you. Okay, so all of this is to say that yes, we can find it on a graph, but sometimes if we're not careful, we might miss the hole. But the algebraic way that we can guarantee this is if we say, discontinuities are only going to happen when that denominator equals 0. Let's find out what they are. And if one of them has the same factor as the top, that'll give us a hole. But if it's only on the bottom, then that'll give us a vertical asymptote. Okay, great. Yes, Nora, what's up?
Will you only have an infinite discontinuity when you have an x squared in the denominator?
No, that's a great question. So for example, can you build me a function where the denominator could be 0 for some value of x?
Do you mean like, let's say I put x plus 3 in the denominator?
Okay, all right. If there's no x plus 3 in the numerator, if we just have like a 1 or something like that, if we wanted to set this equal to 0, that would tell us where the discontinuities are. And so we would get x equals -3. But since it's only on the bottom, like the x was on, like there's no just an x up here. There's no x plus 3 up here. That means that this is going to be an infinite discontinuity.
Okay, that makes sense. Okay, so then if you don't have an x squared, it's going to be just the opposite of your value. So like if I have 3, the -3, the conjugate, basically. The reciprocal, you know what I mean? Like 3, -3. If I had x plus 1, it would be -1.
I would be careful because like, what if you had this situation?
I see. Okay, that makes sense.
Yeah. Like, I know you know how to solve this, but I think it's a slightly different technique than just reversing that number, right? Okay. Okay, I see a question in the chat about where did the x minus 5? Okay, so that's a great question because we've talked about what the bottom of the fraction does for us. But this x minus 5, it came from factoring x squared minus 3x minus 10. Okay, but what it actually tells us is that this point right here is going to be 5, 0. Yeah, so it is where it comes from, and it also tells us that that's where it comes from, if that makes sense. Great. Okay. Now, finding these values are a little bit more pre-calculus stuff, so we're going to be a little bit less worried about that. We're worried more about like, where are the weird things happening? Okay. Okay. All right. So there's sort of a short follow-up question to this, and that is, are are either of the discontinuities fixable? All right. So in other words, if we go back up to our picture for a moment here, is there anything that if this were like, you know, can you like patch it up? Can you make it better? Can you make it continuous? What are
Didn't
our
we just do that with canceling the x plus 2?
Ah, okay. I agree. I would say that this one, this pink highlighted situation, if I were to just drive up and just patch that pothole, we would be in business, right? Then we could draw this whole branch and not pick up our pen or pencil at all. Great. But the connection that I love that you just made, that I want to make sure we all make, is when we were canceling things, right? We said that was like patching in the hole. That means that that discontinuity is fixable. Okay. You were able to reduce some things, and that helped you figure out the y value that should have been there before someone removed it. Okay. However, this, my friends, is not fixable. No matter what we do to this numerator, we can't sort of like cancel out that x. And so because that's not fixable, all right, we don't have to worry about like patching in this value, but sometimes you would be asked to patch in the removable discontinuity. Okay. And in fact, the way we do that is we would do our limits, we would reduce, we would plug in a new value. Okay. So let's go ahead and do that. All right, so the infinite discontinuity at x equals 0 is not fixable. Yes, so that's a great clarification. If it's fixable, it's not continuous until you fixed it. Okay, so we could say here that the removable discontinuity at x equals -2 is fixable. And if we were to fix it, we would have our f of x equals, what did we have? X minus 5, x plus 2 over x times x plus 2. So just like our limit questions, we could reduce those. And we would get x minus 5 over x. And now if we find the limit as x approaches -2, we would get -7 over -2, or 7/2. So this limit, this gives us the y value that should be in that hole. All right. Now, Alexis, I noticed that Utku, is that how you say your name? I don't want to say it wrong.
Yeah, Utku. We can just call me Adam if that's easier for you.
Okay, whatever you feel more comfortable with. Okay, so in response to Alexis's question, it's fixable if we can do something like this. All right, so all the work we did from limits day 1, where we were factoring and reducing that out, what we were doing is this is the y value that we could put back into that function and make it continuous.
But I got lost when you were saying how the x was not fixable. So would that make the problem not fixable since the denominator has the x?
I see. Okay, so this is not fixable because there's no way that I can get like just an x on the top to like reduce out.
So in this case, since you couldn't get rid of the x, it wasn't fixable?
Right, right. So like that's how we would know algebraically. But if we were to look at the picture of the graph, like if I had this and then can you connect this end to this end? If you wanted to connect those two ends, what would it look like?
It would cross the x-axis?
It would, and I would say it might even look something like this, right? Like if we wanted to connect them.
Yeah.
Okay. One of the things that folks probably learned about functions is something is a function if it passes the vertical line test. Does that sound familiar to anyone, the vertical line test? Okay, so the vertical line test basically means like if you draw any vertical line, it should only cross your picture one time at like any given place. So like everything crosses one time, right? But if my graph looks like this, the vertical line that we just drew actually makes it not a function anymore. Like we can't connect this end to this end and still have it be a function. So that's also what we mean when we say that it's not fixable. Yes, Nora, did you have a question?
Yes, our infinite discontinuity is always never going to be non-fixable, and then
Yes.
removable continuities are going to be sometimes fixable, or will they also always be fixable?
They will sometimes be fixable, sometimes not, depending on the picture. And yes, Dallas, I think that's a really great way of saying it. The fixing means like, can we find the limit for that value? Can we find the y value that should go there? Okay. I'd like to
Can
take
I
a
like do a tool in my head, like how you said cancel, also known as patching up? That's fixable.
Mm-hmm.
Okay, because I'm like I try to make like patterns or something to like use while I'm doing a problem. So I'm like, as long as I cancel it, I patched it up so it's fixable.
Love it.
Okay.
Also, I know we're only on day 2, but I feel like you all are the liveliest class that I've had via Zoom, and this is just wonderful. All right, so let's take a look at another example and maybe use that to sort of help the discussion around the fixing. Okay, great. All right, so let's look at example 4 here. We have this piecewise function, all right? And this is not something that a lot of times we are asked to be really familiar with at like the earlier levels, right? Sometimes it's just like the thing that got shown one day in class and then that everybody moved on. But piecewise functions, I think, are actually really important. And so I want to take some time to sort of like help us read what's happening here. So in this particular function, k of x, we actually have 3 pieces to this, okay? In particular, we have 3x minus 2. That's one piece of it. We have 5. That's another piece of it. And we have x squared, and that's another piece of it, okay? The thing with piecewise functions is they don't all happen like at the same time. like at the same x value, okay? So in fact, depending on what x value you have, that will tell you which piece of the function you should be going to. So let's say I said x equals 0, okay? Which piece of the function would I go to? The pink one, the green one, or the blue one? Right, I see blue, I see pink. All right. Alexis, I'm wondering if you can tell us how you chose pink. Because you are indeed correct.
I chose pink because when you're multiplying the 3 by the 0, you get the -2. And then when you're, I thought, I just kind of guessed because like the x is, the 2 is greater than the x. So I was going with,
Okay.
are we getting 2?
Okay, I love the reasoning there. So I want to make sure you all heard what she said, which is that I asked you where x equals 0. 0 is less than 2. Because I'm choosing a value that's less than 2, I want to use the corresponding equation. Okay. What if I said when x equals 1, which one of those 3 colors would we choose? Pink, green, or blue?
The same one.
Yeah, the same one, right? Because 1 is still less than 2. Okay, what if I say x equals 3, which graph should we, or which part of the piecewise function should we use?
Blue.
Blue, exactly, because 3 is bigger than 2. All right. What about at x equals 2? Oops, sorry. Yeah, we want to use the green one. All right. So that's how we read this, okay? There's 3 different ones, but each line tells you when do you use and what you should use, okay? So based on that, I'm going to ask us to come up with whether or not the function is continuous at 2, all right? And so here's how we're going to do this. If x is, oops, if k of x is continuous at x equals 2, okay? So continuous, let's see, earlier we talked about a definition for continuity. What things did we check to make sure we're true in order for something to be continuous? And you can either use the definition above or the one that we wrote out. Okay, so I see that k of 2, whoops, let's do this. Then k of 2 will equal the limit as x approaches 2 of the k function. Right, that was our very grown-up way of saying continuous, meaning that we could just connect right through at x equals 2 and we wouldn't have to pick up our pen or pencil. Okay. Well, let's start with this left-hand side. How do I find k of 2? It has a y value, okay? And what does this piecewise function tell us that value is? Yeah, right? Because we said when x equals 2, if I hand you x value of 2, you're like, that's 5. Okay. So k of 2 equals 5. That means we hope that the overall limit is also 5. Well, how do I find the overall limit if I don't have a picture? Exactly. We use the left-hand limit and the right-hand limit because if they meet at the same point, we're good to go. But if they are offset, then that's not going to have an overall limit. So to find the limit as x approaches 2 of k of x, we first find the right-hand limit. Oh goodness, letters are and the right hand. All right, so this is our left hand limit. This is our right hand limit. So if you were to trace on the graph, I know there's no picture, but if you were to trace on the graph and find out what x is getting to, or what the y value is getting to when x gets close to 2, but you're coming from the left, which of these pieces would you use to help you find that? Whoa. Why pink? How do we know that? Yeah, right? What's to the left of 2 is all the things smaller than 2. In fact, if I were to think about this even as just on a number line, this is 2, I would say that at 2, I would use the green. But if it's bigger than 2, I'm going to use the blue one. And if it's less than 2, I use the one to the left. Right? And this tells us left hand limit, right hand limit, and f for k of 2. Okay, because we're reading the graph from left to right. And so if I want to find the limit as x approaches 2 from the left, I'm going to say the limit as x approaches 2 minus of 3x minus 2. Oops, sorry, no more minus. And our number one tool for finding limits algebraically is just plug that number in. So we get 3 times 2 minus 2, which gives us 6 minus 2, which is 4. Okay.
I have a question.
Yes.
So is the 3x minus 2, is that one always going to, and the bottom one, is that one always, those two always going to be the left and the right, or no?
Well, these functions may change, right? Depending on what piecewise function we're looking at. But if it's less than the value, that will be the left-hand limit. And if it's greater than the value, it'll be the right-hand one.
Okay, I'm gonna write that down so I remember.
Okay, great. All right, I have 30 seconds, I think. What should I put here if I want to find the right-hand limit? Yeah, I'm going to choose the blue function, okay? So because of this minus, we're choosing the pink because that's to the left. And because of this plus, we're going to choose the blue, which is x squared. And now we just plug in our number. We get 2 squared, we get 4. Okay, so here's what we have right now. We have that the k of 2 is 5. And what's the overall limit for this function at 2? Yeah, it's 4. Does 5 equal 4? I certainly think not, right? 5 does not equal 4. And so we would say that k is not continuous at x equals 2 because k of 2 does not equal the limit as x approaches 0 of k of x. Right? That is our very grown-up way of saying that we cannot draw this without picking up our pen or pencil. And that, my friends, is all the time we have for today. But I did want to, let's stop this recording for a moment.